Today, I'll be looking at this Godot project called Alix as part of a new Godot code review series that I'm doing on this channel. The goal of this series is to take a look at projects that you submit, inspect the scene structures and the scripts, and offer my suggestions and critique for what's done well and what could be done better. Hopefully, it's educational for you, the viewer, and helpful to the developer that submitted. This project comes from Olivier from France, and the developer's social links and Steam page are linked in the description below, so check those out, support the developer, and let's go ahead and open up the project and see what we've got going on. Okay, so right at the bat, we've got some errors here, and it looks like this is just because I don't have something called GDScript formatter in place. That looks like I might need to install something third-party, but I'm going to see if I can safely ignore that for now. And speaking of plugins, let's just go ahead and look at the project settings, and let's take a look at the plugins. So this project is using plugins, I would say, quite heavily. I haven't used nearly this many plugins in a project, which is fine. You should absolutely use whatever plugins are going to help your development. I probably should actually be using plugins more than I do. But one of the most notable ones we have is Behave, which is a behavior tree plugin. And the developer, as part of this form submission, mentions that we want to take a look at the Minotaur behavior tree as well as some state machines. But before we get to that, let's just take a look at the general project structure here. So it looks like we've got a pretty well organized project here. I mean, I can go to entities character and let's just see if we can find the player within here. Yep, there's the player. So this is all very well organized. And it looks like everything that's related to the player is grouped as either a file underneath the player directory or as a subdirectory. So we've got player assets in here as well. Of course, we've got NPCs, one called Angelstone. Let's just open this up and take a look at what this looks like. And yep, that looks pretty much like what I'd expect it to be. There's an Angelstone. And we've actually got very sophisticated scene structures here with all kinds of custom icons, which actually is very nice. I like that a lot. So one thing that I'm noticing here is that this appears to be using inheritance. So all of these nodes here that are in yellow are coming from a base scene. So let's see if we can open up the base scene. Okay, so we've got an NPC base. So there's something happening here, which is a little bit, I won't necessarily say odd, but we've got a composition-based design here. So we've got shadow component, visual move component. I don't know what any of these things do. I mean, obviously the shadow component seems to be pretty straightforward. If I turn this off, yeah, the shadow goes away. So that makes sense. But typically, I don't personally use inheritance with composition. I don't mix those two things together. So it's kind of interesting in this project how we have a base NPC, which is composed with components, but then we have, let's say, concrete NPCs that implement or extend that base script. Inherit is the right word, and then override things as necessary. So it looks like one thing that is not overridden here is the sprite, the visuals. So this is unique to this scene, and the state machine states. So here's another thing that I'm noticing. The state machine is implemented as nodes rather than pure scripts. So maybe that's something that we'll take a look at later. Now, one thing that I'm noticing here is that there is a sprite here for this NPC base, but I actually don't see a corresponding sprite node in here. Oh, I see. So the sprite is coming from this visual move component here. So if I toggle this, that actually disables the sprite visibility. Let's open the visual move component. Okay, so that's where this is coming from. So how is that overridden here in the Angelstone? I'm not actually sure. Oh, it's just hidden here. Okay, so there is the first problem with using inheritance with composition like this is that you're going to end up with these extra nodes, in this case, the Angelstone, which you have to manually disable the visibility of these components. Now, that's not necessarily a problem, especially if, you know, you've got like an Angelstone here that is just kind of like an odd NPC that needs a lot of the behaviors of the NPC, but not all of them. So I wouldn't necessarily say that this is a problem. What I would say, though, is that if I was personally approaching this, I probably wouldn't use inheritance. I would probably just include the components that I want to include. Now, I don't know how many NPCs are actually in this game. It's quite possible that using scene inheritance is actually saving a lot of time because otherwise you'd have to set this all up manually. But there's a lot of stuff here that's not used, like actions I bet you this idle state basically does nothing in here. So let's see if I can figure out what this does. Okay, so here's how the state machine here is working. So there's a state machine root node which accepts a bunch of export variables. Now, what this ends up being is this is the context for all the individual states. So there's a base state which has a reference to all of these things. And if I look at the state machine here, we can see that here's all those export variables. So those are things that presumably any state is going to need. And then when the states are set up, here's what's happening. So on ready, the state machine node, which is this one here, is actually iterating over all of the state children and assigning all those variables. So there's kind of a dependency injection going on here where all of the children are receiving references to the state machine state. So this is fine. So let me just preface all of my feedback by saying you should absolutely do whatever works for your game. But all I'm going to do is I'm just going to point out problems with this architecture so that you are informed what the various pitfalls are for this. So one pitfall here with this state machine implementation is what happens if I have a very unique state that only needs something that that state only ever needs? So let's say that I have another component type in here for a very specific state that exists on a very specific entity. Is it worth cluttering up the export of all of those state machines across the game? So that's one question you might ask. Another question you might ask is the opposite question, which is what happens if I just have like dozens of things that I need access to? Do I really want to have to set all of those up? And a lot of that is mitigated by having the Angel Stone, for instance, extend from this NPC base, where you can just configure all of those things ahead of time before you inherit from this scene, right? So there are considerations here about inheritance to be made, but you just have to be aware of that pitfall is that this list could grow to be very unwieldy at certain times. And also, this is not very amenable to having like one-off variables that you might need. Let's take a look at the stages. So we've got exterior base. All right, so I don't know what this is. So this is an exterior template. So this looks like all the things that are needed to create an exterior environment. So this game is an RPG, so there are going to be lots of environments to be done. Let's take a look at a more specific one. Let's try northarea.tscn. Okay, so we have a very beautiful tile set here. I'm not sure if this is an asset pack or if this is hand-drawn by the developer. Regardless, it looks beautiful, and I have nothing against asset packs. If you make it work, then you make it work, right? But if it is hand-drawn, then yeah, this is very, very beautiful work. So we've got the overworld here. We can see how this exterior base has been used. So this north area inherits from the exterior template, and then obviously we've got all of our different things. So we've got where is this stairway? So little tip, if you highlight a node and press F, it will bring that node into focus in the viewport. So we've got some stairs here. So I'm assuming, not to go too deep down a rabbit hole, but I'm assuming that colliding with a stair, so these stairs have colliders here. I'm assuming that this does something to change the z-index of the player or the elevation of the player. So if I take a look at this cliff stair, let's just see what's in here. So we've got lower trigger layer here, and we've got a layer trigger. What does the layer trigger do? Yep. So this looks like exactly what I was saying it would do. It looks like this is changing the player's elevation layer when colliding with the stairs. So that must be used for rendering purposes. So that's very interesting. But back to this north area here. This is a very effective way of actually setting up your environments. I would recommend considering using inheritance for environments because typically speaking, you're going to have all of the same elements in every environment, and setting up things like tile maps and tile map layers every time, it's not really easy to componentize or turn into components, and it just lends itself better to inheritance than other things. So this is a very good use of inheritance, I think, is using this exterior template. Now we've got a bunch of bushes here, and these bushes, it looks like these bushes are destructible. So if I look at the bush here, we've got health components, die components. So this is a dead giveaway that these things are going to be destroyable by the player. So all in all, I'm not going to open up every single scene in the project, but the reason I went through all of that is to show you what a sophisticated project looks like. So I have my personal bits of feedback here, but I would say generally this project is very, very well constructed, very well organized. I have only been in this project for like a grand total of 15 or 20 minutes now, and I already have a good idea of where to find various systems. I know where the NPCs are. I know that the NPCs extend from an NPC base. I know that the exteriors extend from an exterior base component. I know that there's an elevation layer system with the player, and I know that there's a library of components to use that is used to compose things like bushes that are destructible or enemies. So I'm actually curious. Let's just go look at one more thing, which is the skeleton here. And this probably extends NPC base as well. Okay, so we have a different base here. We've got an enemy component base. So I guess I was wrong there. So the NPC base is probably for interactable, friendly NPCs, whereas the enemies are combat oriented. So without looking at the code too much longer, let's go ahead and run the game. And we'll just take a look real quick at what the gameplay looks like. We've got some debug tools here, which is very helpful to do. So we've got Aurelia Island, Romaine and Alix's room. So Romaine, from what I got from the developer, is the main character, and his sister is Alix. So we've got a dialogue system here. That's very nice. Again, I'm not here to review the gameplay. I'm not going to offer my game design feedback. What I'm really here to do is just offer code feedback. So the developer of this game specifically mentioned that I should look at the Minotaur. So let's go ahead and just search for Minotaur here. We've got a Minotaur scene, and I actually didn't get any instructions about how to test the Minotaur combat, which is totally fine, by the way, because I think part of a good code review is me going in somewhat blind and trying to understand the structure of the project. So what I'm going to do to figure out how to test this Minotaur here is I'm just going to search for the Minotaur in the file system here, and then I'm going to search for view owners, or I'm going to click view owners here. And that tells me that, oh, there's an objects test in stages. So this looks like a test room. And if I zoom out a little bit, it looks like we've got all kinds of different things to test. And the Minotaur is used here. The player's already here. So I'm not going to say too much about the test scene here. I think that test scenes are perfectly fine to just be hodgepodge messes of random nonsense. I don't think that there's necessarily any sort of rhyme or reason to all the elements that are placed here, which is totally fine because it's just a test environment. So let's take a look at how the game looks and feels inside of this test environment, which I'm just going to run with F6 or play scene. All right, so it looks like we've got some debug drawing for the Minotaur. Maybe there's a field of vision. So maybe since the Minotaur's back is turned, yeah, okay. And if I can hit the Minotaur, let's see. Yeah, spacebar to attack. Okay, cool. So we're going to take a look at the Minotaur specifically and see how this guy is functioning. So this is where the behave add-on comes in. We've got a behave tree here, which has all kinds of behavior tree nodes. If you don't know what a behavior tree is, it's basically just one strategy for defining enemy AI. And this is using the behave plugin, which as far as I can tell is a very popular plugin for doing behavior trees. Now this looks like a fairly sophisticated behavior tree here with lots of nodes. And so I actually don't know how behave is supposed to work, but it looks like perhaps as part of the plugin, getting it to work, you're supposed to implement your own sort of behaviors here. So this is a sequence. So again, I'm not terribly familiar with behavior trees. I've only implemented them like once in a prior game many years ago, but a sequence basically does things in a sequence. And there's like different decorators that you can use to invert values and so on and so forth. Random selector will select a random sequence here. And basically what happens is you start at the root behave tree here, and you've got a tick rate here. Now, I don't know what this is. This might be 1 tick per second, or it might be 1 tick per frame. I'm not actually sure. It looks like it might be 1 tick per physics frame. But again, I'm not entirely sure. And of course, behavior trees also need what's called a blackboard. And a blackboard is just a container that contains a bunch of data that your states might need. So if I had to guess, what I would say is that things like this long-range lightning attack, if I were to open this script, it probably has some values that it's pulling from the blackboard to use the attack. So let's take a look at it. Okay, so this is actually a built-in behave script. So we don't actually want to change anything in here. This is a sequence. So this is just the name then of the node of the long range lightning attack. So let's see how it's actually getting the specific player information. So we've got a get player position here. This get player position is, okay, interesting. So this get player position is a custom AI action, it looks like, inside of entities. and more specifically inside of Minotaur. This might be the only implementation of a behavior tree in the game for an enemy. So I think that's probably why this get player position is inside of the Minotaur directory. But if you were to take these behavior trees and use them across different entities, you'd probably want to make this more generic so you can use it. But I think it's just because it sounds like the developer is just testing out behave for the Minotaur specifically, because we could also see earlier from the video that the developer has state machines as well. But here's a good example of how the blackboard is actually being used. So the blackboard here is basically, it looks like just something that contains a dictionary and has various methods of getting or manipulating or setting the data in that dictionary. And if we go back to get player position here, which extends action leaf, this will set a blackboard value with key player position as player.global position. So this is how data gets onto the blackboard, and part of a behavior tree is you actually do need to return success or failure for every node. Are these just Boolean values? No, this is an enum. So success, failure, running. So running is when ticked, and success, failure, I guess, are for instantaneous nodes. So that makes sense. So in here, we're going to return failure if we don't have a player. Otherwise, we're going to return success. And we're actually getting the player from this utils singleton, it looks like. And if I look at the get player method, this is just returning get player in scene. So I'm not sure about this method of finding the player, because what this is doing is this is taking a whole scene node and then trying to find any, so this is trying to find any player in the entire node structure. And this is doing it recursively. So find child is recursive by default. So we can see in the docs here. So what this is going to do is this is actually going to iterate basically over the whole tree, or it can iterate up to the whole tree depending on how deep the player is in the tree. I don't know why the developer is doing this. There may be a good reason for it, but I would probably just use a group instead. And what people need to know about the Godot groups is that find child scans up to all of the descendants of the supplied node. Grouping works differently because if you assign a group to a node, that's actually stored as a hash map under the hood. So if you add the player to the player group, it actually becomes a pretty much instantaneous operation to find the player with that group name, because all it does is just a hash map lookup. So it looks for all the nodes that have the group player and it returns them. It's just a map. So it doesn't do any scanning or recursion over the scene tree at all. So I would recommend just avoid find child. I really don't think there's ever a reason to use this. Again, maybe the developer does have a good reason for using this, but I generally regard using find child as just something that you should avoid if possible. But again, that's just my opinion. I would definitely prefer groups rather than doing that recursion there. But that's how we're getting the player. And so that is set down here in this get player position. And then we've got an is player in range. This is going to be a custom script as well that just returns success or failure based on whether the player is within range. So you can see how this behavior tree works is that it assigns the player position to the blackboard first, then it checks if player is in range, and it uses an inverter decorator, which inverts the result. So this inverter decorator just returns failure if the child node returns success and vice versa. So I think what this is doing here is this is player in range is configured to have a range of 100. I think what this inverter decorator is doing is basically saying abort the long range lightning attack if the player is within 100 units. Because what this is doing is this is going to check if the player is within 100 units, that's going to return true. It's going to be inverted here to false, and that's going to break the chain, right? So what we want is we want the player to be outside of the range of 100 so that this will ultimately return a failure status. Then it will be inverted by the inverter decorator, which is going to be inverted to success. And then that means it can continue on. So basically the way this works is this has to return success, this has to return success, and then so on and so forth. If any of these ever return a failure, this sequence gets aborted. Now, if I had to guess, turn to player probably always returns success. Okay, it returns failure if there's no player. Okay, that makes sense. Play sound probably always returns success. Yeah, so there are definitely behavior tree nodes that you might just want to succeed always, but that's generally how a behavior tree works. So let's just talk about whether you should use behavior trees or a more traditional state machine. I personally don't think that behavior trees are that useful because they have to be so granular as to require this kind of entire scene setup here. And I'm already seeing things that look like they're probably tricky to manage. So for instance, this modify speed, this is something that I think is very hard to do with a behavior tree, is modifying the current state of the entity, particularly as it relates to speed and things like that. So out of curiosity, I'm just going to go ahead and open this modified speed up. Yeah, so there's some weird stuff going on here, as I kind of suspected. So we've got an action type here, which basically seems to be deciding how this value gets applied. And we're checking down here during the tick, based on that action type, we are saving the speed change or restoring the previous speed change, or there's a lot of state management happening here inside of a behavior tree node, which generally makes me uneasy, especially seeing all these strings in here. So again, if it works, it works. But this is one of the things that I don't like about behavior trees is it's very hard to modify entity state from within a behavior tree. At least maybe not hard technically, but it's hard in the sense of like doing it in a reliable, bug-free way, a way in which it's clear what's happening and tracking the flow of data and all that stuff. It just makes me very uneasy generally. Regardless, it's just you need to have all of these nodes configured just right for your entity, which takes a lot of setup effort for sure, but also I'm wondering how easy this is to debug. I'm not sure if Behave has like a debug view. So let me see if I can figure that out. So I'm gonna run the objects test again, and we're gonna take a look at this. So it looks like we've got a Behave tab inside of the debugger tab here, and we can select this Behave tree. I'm not sure, this must be the Minotaur Behave tree. So we can actually see the Behave tree running here. So that's very useful. So that certainly makes Behave vastly preferable to your own implemented behavior tree. Just this view alone makes it worthwhile. So we can see that it's choosing to do a random sequence here, attack 2, attack 4. So I wish I could show this at the same time as the screen. Maybe I can. So let's just take a look at this. Yeah, so it's got attack 2. It looks like it's choosing different attack animations. That's more of a stab animation. It did a stab animation again. Then it did a swipe animation. So you can see how it's choosing that. And it's got a cooldown decorator here, which seems to, yeah, so that cooldown decorator is preventing the random composite sequence from being able to run. See, when this is red and it has a failure status, it does not select an attack. So that's cool. Let's see if we can trigger that lightning attack. So where is the lightning attack here? Long range lightning attack. Let's see if we can get this to trigger by running away. It looks like we may have lost aggro. Oh, there it goes. There's the long range lightning attack. So yeah. So I would say that, yeah, the behavior tree, if you're going to do a behavior tree, probably definitely consider using something like Behave just for the debug tools here, because that's going to save you a lot of time. But I still probably would not use a behavior tree for this kind of game. The situations in which I would personally use a behavior tree is maybe if I had a game designer working with me who was not particularly technical and needed some like GUI way of designing enemy behaviors. That's where I think behavior trees can be very useful if you need to empower non-technical people who don't have much programming experience to design entity behaviors. But if I'm working on this solo, I would much prefer a state machine implementation. So I'm actually going to see if I can rewrite at least some of the Minotaur as a state machine, and I will get back to you and show you how that looks. Okay, to demonstrate how the behavior tree might look if it was implemented as a state machine, and a state machine that's a pure script rather than a state machine that uses nodes like we see elsewhere in this project, I just took about 30 minutes and I used my callable state machine implementation to write up a couple of the states to compare and contrast how the behavior tree looks to how the state machine script looks. Now, for the developer of this game, I'm not going to give you a recommendation on which you should use. You have a very sophisticated project here, so you should use whatever you are most comfortable with. But for anyone watching, I hope that this exercise is useful in seeing the differences between how the behavior tree works and how the state machine works. So I've actually created a Minotaur dupe script here, which is just alongside the old Minotaur script, and I'm using the same scene. So I just created a duplicate script and attached that to the Minotaur scene so that I can have different behaviors or different functionality in here. And what I did is I pulled in my callable state machine implementation, which is just called callable state machine. And all this does is this this basically is just a state machine that uses callables, which are references to functions, as the states themselves. And the benefit of doing this is that when I call update in the state machine, it checks what the current state is and then just invokes that function. So your functions become states, and you can also have enter states and leave states. So I'll show you what I've done here. So I've implemented basic Minotaur movement. So I've added the idle state and the patrol state and the chase state. I didn't add any attacks because I didn't want to go overboard here. This is a good enough example to show how this looks different. So of course I also need in physics process to call state machine.update. So that's like the ticking mechanism for the state machine. And so we can take a look here. So the way that this state machine is configured is I call state machine.add states, and then I supply the normal state, the enter state, and the leave state. And if I don't have a enter or leave state, I just use an empty callable object by creating it like so. So we could see that I've got an idle state that has an enter version of the state, a state patrol that has an enter state patrol, and a state chase that has enter state chase. And then I set the initial state to state idle. Now, the only thing that I needed to add to support the idle state was this patrol wait timer, which I've set to 2 seconds. That just basically stops the Minotaur from going to the next patrol point for 2 seconds after finishing the last point. So how does this work? State idle is actually a function. I can control click to it. It's right here. And in the state idle, first, when we enter the state idle, it triggers the idle animation. So the Minotaur is always going to be in the idle animation when entering that idle state. During that idle state, we decelerate the Minotaur and call velocity component.move. I'm not going to get into how this works, but basically this velocity component just has methods for maintaining a velocity value and accelerating, decelerating the velocity, and then applying that movement to a character body 2D, which is what's being referenced by self here. Then I have this isPlayerVisible function. This is lifted right out of one of the custom behave nodes that the developer of this game implemented. And this is just returning if the player detection zone can see the player. So remember, there's like a visibility cone for the Minotaur. So if the player can be seen, we're going to change into that state chase state. Otherwise, we are going to check if that patrol wait timer is stopped, and we're going to change to the state patrol. If neither of these conditions are satisfied, then the idle state is just going to keep running, which is just doing this deceleration. So the Minotaur is just going to come gradually to a stop while neither of these conditions are satisfied. When we enter the state patrol, we trigger the run animation so that we put the Minotaur in the run animation. And then in here, this is just movement code here. It looks kind of like a lot because we're using a pathfinding mechanism here to move the Minotaur, but this is very simple. All it's doing is just getting the patrol points, and those patrol points are actually down here in this objects test. So this is the test level. The patrol points are here. They're just marker 2Ds. So they're nodes, and that point is being chosen based on the current point index, which is just a rolling number. So it will be either 0 or 1, and then it rolls over to 0 again. Grab the global position, set the navigation agent target position, get the next path position, so on and so forth. So basically, this is all just movement code. This is basically just saying, hey, get the direction of movement that I should go along the path, and then accelerate the Minotaur. And then there's a distance check here, which is that if we are within the distance of the path point, we are going to start the patrol wait timer, change back to the idle state, and we're going to increment rolling over that current point index. So basically, as soon as we're within, I believe, 10 pixels of the patrol point, then we're going to go back to the state idle. Now there is a condition up here. If player is visible, then we're going to change into this chase state. And the chase state is basically the same thing. This is just using a pathfinding mechanism through the navigation mesh. And instead of targeting a patrol point, it's targeting the player position. There is another check down here, though, that if the player is more than 100 pixels away, then we're going to change back into that state patrol. So we're just going to resume the patrol. One of the benefits of doing this as a pure script is that I have all of the context that I need. So anything that is part of the entity here, any of these nodes, I have access to that right at this root script level. With a behave tree like this, I need to supply a lot of that information through the Blackboard or through export variables and so on and so forth, which is fine. I mean, you can certainly do that, but in my opinion, it's really nice to just be able to have all the context you need for a state machine readily available without having to go through the hassle of worrying how to get the information where it needs to be. The other benefit of that is that I think the logical flow is a lot easier to follow in script form than in the behavior tree form. Now, maybe there are some people that disagree with me that prefer the more visual presentation, and that's totally fine. But for me, I find it much easier to read this state idle, see that this is being decelerated, see what the conditions are, all in line, all in order. Actually, these states are not that large. So this state patrol is capturing this entire branch of the tree down here. So this patrol tree, all of these nodes are being captured by this block of code. So there's a question about the verbosity of a behavior tree like this. The fact that it takes a while to set up by adding all the nodes in the right order, then you also have to write your own custom behaviors in here to return success or running. All of that can be condensed down into this many lines of code for the same exact functionality. So again, I'm not making a recommendation to the developer about which technology to use. Also, the developer of this game is actually using a node-based state machine, which I recommend against for a variety of reasons. One reason is because, again, passing around the information that you need for the states has a lot of the same problems as the behavior tree. You need some kind of blackboard or some way of injecting the dependencies into the individual state nodes, and then you end up with fractured states that have partial context all over the place. And the problem too is that the states don't end up being reusable that often. Now, I haven't taken a whole in-depth look of the state machine in this game. This game may actually make effective use of like generic states so that they're reusable across nodes. But I generally find that NPCs and enemies tend to have enough variation in their behavior that the only way to really genericize or make generic their behavior is to use a behavior tree like this. But then the behavior tree is more cumbersome in my opinion compared to just a raw script. So personally, when I write enemies for my games, like in Gunforged, I just write the script in a bespoke manner right there for the entity. And I do, pull out and genericize the things that I can make generic. But for the most part, I don't have a problem even if I repeat myself a little bit across lots of entity scripts. It's a much nicer developer experience for me at least. And just for the sake of completeness, let me go ahead and run that test scene so we can see that this is indeed working the way that it should be working. I don't know if I captured all the numbers correctly. I don't have any attack states in there and so on and so forth, but let's just take a look at this. So you can see that the Minotaur is going along his patrol. Again, this is using my state machine implementation that I wrote here as an example. And if I were to enter this visibility area, then the Minotaur is going to go ahead and chase me. And we can see that the animation states are correct. It follows me, it path finds around obstacles, which you can see by the debug draw here. And if I leave the range, the Minotaur will return to the patrol and just go about his business. So that is how you can alternately accomplish the same thing as a behavior tree or as a node-based state machine with just a raw script. So I hope that gives you some idea of your options that are available to you in terms of enemy AI behaviors. So that's going to be it for this code review video. Please check out the links in the description below for all of the developers' information, social media links, and also the Steam page. This is the Steam page here for Alix. Go ahead and wishlist it. This project is definitely very sophisticated. I don't really have any, I don't think, useful critique for the developer, but I hope it was helpful for you all to see what a sophisticated project and mature project looks like. And I hope that my little foray into the exploration of the different aspects of how the game is structured, as well as the state machine implementation, I hope that that was useful to you, or at least that gave you something to think about. So again, please check out those links in the description below, and also check out my stuff. Gunforged is available on Steam as well. You can purchase that to support my work, or you can purchase one of my Udemy courses to learn how to build a complete game in the Godot engine. There's also a link in the description below to submit your game to be potentially reviewed for this series. It's a Google form link, so look for that in the description below if that's something that you're interested in. Thanks everyone for watching. Thanks for your support, and especially thank you to the developer for being the inaugural project on this code review series, and I will see you all in the next video. All right, bye-bye. Thanks for watching this video. If you want to support my work, you can purchase one of my courses, you can purchase my game Gunforged on Steam, and you can sign up for my email list at firebelly.com. All the ways that you can support me are linked in the description below.